Hello, I'm Rob Gill, and I'll be presenting a series of short presentations on the technology of diagnostic ultrasound. We're going to start by looking at the nature of ultrasound itself. Ultrasound, as you may guess, is a form of sound. The only big difference between ultrasound and the kind of sound we can hear relates to the frequency. But if we think first about the nature of sound waves, they consist of pressure variations. So when sound is traveling in the air pressure is being increased and decreased in a cyclic fashion, and that propagates through the air as a sound wave. For example, a loudspeaker will compress and then decompress the air in an oscillating fashion. This will create sound waves which will travel through the air, reach our ear and set the eardrum vibrating, which we then experience as sound. Ultrasound is exactly the same, except that it operates at much higher frequencies. And of course it's traveling through tissues rather than through the air. Let's look at how the ultrasound wave is generated in diagnostic ultrasound. A probe is placed against the skin surface. The probe contains something called a transducer, which is the active element which can actually generate and receive ultrasound. So the transducer is vibrated electronically, and this transmits the vibrations to the skin surface, which causes pressure oscillations in the patient's tissues. The oscillations are extremely high frequencies, typically 1,000 times higher than audible sound frequencies, and the sound then travels through the tissues as an ultrasound wave. As you probably understand, ultrasound imaging is based on the idea that you transmit a short pulse of ultrasound into the patient's tissues, and then that ultrasound interacts with the various structures within the tissues, creating echoes. Echo energy travels back to the probe, it's detected by the transducer, and converted into electrical signals which are processed by the machine and displayed. This shows us the pressure variation at one particular point in the tissues. So we're looking at a point in the tissues which an ultrasound wave is passing through. The vertical axis in this graph is tissue pressure, and the horizontal axis is time. The center line represents the average pressure in the tissues, which will be essentially the same as the external air pressure. So you can see that the pressure is increasing and decreasing in a cyclic, oscillating fashion. When the pressure is increased, we refer to that as compression. When the pressure is decreased, that's rarefaction. I've marked two important parameters here. One of these is the amplitude. So that's the actual amount by which the pressure increases and decreases due to the presence of the ultrasound. This, of course, is going to relate to how much energy is being transmitted into the body, and therefore it will relate to the question of whether or not there is potential damage. There may be potential damage to the patient's tissues. So the amplitude relates to the exposure of the tissues, which relates to the question of the safety of ultrasound. We'll look at that in a later presentation. The other parameter is the period of the ultrasound wave, which is the length of time that one cycle of oscillation takes. So it's the length of a single cycle of the ultrasound oscillation. It's very short. For example, if we are using a typical frequency of 5 megahertz, then the period would be 0.2 microseconds. This graph may look the same, but in fact it is showing us pressure variation with depth into the tissues at one particular instant. So we're looking now at one particular moment in time and the way in which the pressure varies with depth into the tissues. The pattern is exactly the same because, again, there are areas of increased pressure and areas of decreased pressure at any one instant. I've marked one parameter which is important, and that's the wavelength. I've labelled it with the Greek letter lambda, since this is the conventional symbol used to represent wavelength. So the wavelength lambda is the length of one cycle. We'll see shortly that the wavelength is quite small, and it's very important because it relates very directly to the resolution of the ultrasound image. Now, there are some simple relationships which you may well be familiar with, and they are shown here. So the first of these is that the propagation speed, which I'm representing with the letter C, again following convention, the propagation speed is equal to frequency multiplied by wavelength. Now, the propagation speed is approximately 1540 meters per second in average soft tissue. So the propagation speed is a fixed quantity, which shows us, of course, that the wavelength is inversely related to frequency. And I've rearranged the equation to show this, that the wavelength is equal to propagation speed divided by frequency. And this, of course, allows us to calculate what the wavelength will be for a given frequency. The other equation I'm showing here is the equation that describes the actual pressure variation with time at one particular point. And I'm showing you this just for one reason, and that is to emphasize the fact that there is the sine function there. So that's the trigonometric sine function, and that describes the shape of the ultrasound wave. For that reason, it's referred to as a sine wave. So the smooth oscillating waveform that I've shown you in the previous diagrams is referred to as a sine wave. Later we'll see that there are circumstances where the waveform changes in shape, and this then introduces harmonic frequencies which can be exploited in special ways that we'll talk about later. Here's a graph showing a few values of the wavelength at various different ultrasound frequencies within the diagnostic range. Note that the diagnostic range of ultrasound frequencies is typically from about 2 megahertz to about 20 megahertz. Megahertz, of course, is millions of cycles per second. So the wavelength you can see at all these frequencies is less than 1 millimeter, and that's good news because that suggests to us that under optimum conditions we can hope to achieve resolutions with ultrasound that are sub-millimeter. So to summarize, ultrasound is simply sound but operating at much, much higher frequencies than we can hear, ranging typically from about 2 to 20 megahertz. The reason for these high frequencies is because then the wavelength is very small and therefore the resolution is good. It's a very simple relationship. The higher the frequency, the better the resolution will be. The period is 1 over the frequency. It's the length of a single cycle. The propagation speed, as I mentioned, is around 1540 meters per second. It varies slightly from one tissue to another, but that's the average value, and that's the value that is coded into the machine's image formation. There are variations, as I said. For example, fat typically has a lower propagation speed. Muscle has a slightly higher propagation speed. The wavelength, as I've shown you, ranges from approximately 0.1 up to a little less than 1 millimeter, depending on the frequency that's being used. As I said, the higher the frequency, the smaller the wavelength, and therefore the better the resolution. And finally, the other important parameter is the amplitude, which relates to safety questions that we'll look at later. So just a quick look at the wave nature of ultrasound, how it is generated, and some of the important parameters.